Okay, now we've seen this very innovative approach for improving the behavior of, or the performance of still a radial flux machine, and that's a very good, let's say, change to the further topic. How can we improve machines by changing their topology? And I'm very happy or very interested to hear from Daan Moreels on the new topology he proposes, the axial flux motor topology, and how he solved that. Will it dominate the future? That's his topic. I looked at the CV of Daan Moreels, and he's from Belgium, where he's got an engineering degree, but he changed, or his career is actually really pursuing new technologies as a technology entrepreneur. He's worked at various tech companies, and he's co-founded different companies. One was a cloud computing company with GPU-powered virtual workstation, so that's completely out of the scope what we do normally look at here at Motor Summit. But it shows this entrepreneurial spirit of Daan Moreels. And since 2016, he's working on a new challenge called Magnax, where he develops and industrializes a yokeless axial flux motor technology. And I'm really looking forward to hear about the advantage and ideas he's following through with this technology. Let's hear.
Hello everybody, my name is Daan Moreels from Magnax. Magnax is a technology startup from Belgium, 25 people, and active in the development of yokeless axial flux motors. So we believe that axial flux motors are basically ready to displace a large amount of traditional EV motors, radial flux motors as we call them, and as such want to give you a small introduction into the technology. As a first intro, on a theoretical level, we give you an overview between, or a comparison between, the typical EV topology, radial flux motors, and axial flux motors. So why do they call it radial flux motors? Is because the flux in a radial flux motor, which is leaving from the rotors, is going through the yoke and taking a 180 bend and then back. So the flux is basically in a radial flux motor perpetual to the axis of the motor. In a yokeless axial flux motor, like in our scenario, the flux is going from the magnets on rotor disc 1 through the cores to the magnets on rotor disc 2 and back. So it's in the same direction as the axis of the motor, and that's why we call it a yokeless axial flux motor. Typically, the axial flux motors are smaller in axial length, shorter in axial length basically, more like a pancake situation, and also more effective in electromagnetic sense. So that has been proven in academic world. The problem, of course, is that it was quite tough until today to basically put them into series production. If you look at the three topologies here on the right-hand side, is that the first topology is a typical radial flux motor, where you always have a yoke. So the yoke is basically in a metal tube, which is used to fix the cores, the teeth basically, and also to guide the magnetic flux. In the middle you can see a yoked axial flux motor design, which is basically one rotor disc in the middle and two stators, one on each side. Each one of these stators basically has, of course, a number of teeth and a metal plate which is used to fix these teeth, these cores. The reason for this yoke is because it's pretty easy to put into manufacturing. The yoke is used to basically fix the magnetic cores, to guide the magnetic flux, and also some companies integrate cooling channels, water channels in the yokes to keep everything cool. The problem is there is still quite some isolation between the cooling fluids and the thing that has to be kept cool, which is basically the coils. So from a cooling point of view, not the most effective way to cool a motor. At the right hand side you can see the Magnax design, which is an one stator dual rotor configuration. So the stator in the middle is without a yoke, so we had to find ways to fix the cores and to keep the cores cool. So we use oil cooling, but we can also use water and air cooling if necessary. So in this topology, we have basically one stator in the middle and two rotor discs, one on each side. We see that this is the most effective topology in terms of power density, but also in terms of efficiency. Generally, you can say that the power density of a yokeless axial flux motor is 4 times more than a radial flux motor and 2 times more than a yoked axial flux motor, as you can see here in the middle. The main reason is the absence of a stator yoke, which is basically that weight that you have to wear. It's also a lot of iron which is gone, which is beneficial for the iron losses, which is important for the VLTP area. And also the cooling effectiveness is of course very important. So Magnax has patented a number of very fundamental elements concerning fixing the cores and concerning cooling these stators. In the next slide you can see the historic evolution of our motor technology. So already in 2015 we developed a smaller version of the motor, not cooled at all, 4 kilowatts, and we also developed a prototype for a wind turbine generator which is in diameter 1.6 meters diameter, axial length is 140 millimeters, and has already proven also that on a large scale, a bigger size, that the power or torque density is much higher than the typical situations. Like in this case, an induction motor plus gearbox situation, together about 3 tons for this torque level, but compared with direct drive radial flux generators, it's a factor 4 to 5, where they are higher in weight, where the yokeless axial flux generators are 4 times to 5 times lower in weight. So typically the axial length of yokeless axial flux motors are situated between 80 millimeters and 140 millimeters. So it doesn't change a lot when you increase the size of the machine, but quite effective in terms of torque and power density. To prove that on a smaller level for high-speed machines, we also compared our motors or prototypes with the current best-in-class radial flux motors. In this case, the Tesla Model 3 rear drive motor in the rear drive unit. And as you can see, for a similar diameter, around 290, we are much shorter in axial length, generate more torque, generate more power. So we went with this prototype up to 325 kilowatts peak. The system or the motor was able to go higher in power, but we were capped by the test bench basically. And with the weight, in our case of 25 kilograms, we arrived at a power density of 13 kilowatt peak per kilogram, while the Tesla Model 3 motor arrives at around 5.2. So we already proved 2.5 times more peak power density compared with the current best-in-class motor from Tesla, which is not only best-in-class motor for a radial flux motor in terms of power density, but also in terms of cost effectiveness. Cost is another important factor. If we have been working on the manufacturability of our motors significantly to prove that we can produce them by using standard automated production processes. So that's an important element that has to be taken care of course. The next thing for mass-produced motors is how much material you use for a certain power rating. And here you can already see, compared with the Tesla Model 3 motor, we use less magnet and copper material, also iron material. And if you know that magnet plus copper accounts for around 40% of the cost of a mass-produced motor, you can already see that from a cost perspective, our motors are also quite interesting. Another advantage or element which is coming from the design is a lower amount of iron, which is beneficial for the iron losses. So if you look at the next graph from Vallejo, is that you can clearly see that iron losses are quite important for the VLTP area. If you look at the torque versus RPM area, in the VLTP area, iron losses are dominant. So if you can reduce amount of iron significantly, you reduce our amount of iron losses significantly, and you can basically increase the efficiency on the motor level. and as such also increase the range of the vehicle by itself. So that's very clear. It comes by design. We have been calculating this specifically for a BMW i3 motor. And you can see the difference in efficiency map right here. So in our case, the right-hand side, the high efficiency deep red area is very well aligned over a broad RPM range with the WLTP. In the case of the radial flux motor from BMW, you can see that there is clearly a mismatch in terms of efficiency, which basically results, according to our calculations, in 8% more vehicle range that we can get if we would put our motor into the BMW i3 vehicle. If you account also the smaller and more compact, the compactness of the axial flux motor, and use the additional space that you get for battery cells, you can go up to 25% more vehicle range by simply using a yokeless axial flux motor. Now, how we are going to combine our motors with in powertrains or integrate them in powertrains? So we basically can use existing gearbox systems, like here the Tesla Model 3 lay shaft gearbox. We are working on designs together with partners where we are using 2-speed gearboxes for torque factoring purposes. You can see the compactness of our motors brings benefits for the complete rear drive unit. And also because we have a very long high efficiency area over a long RPM range, we simply do not need a second gear in most circumstances, especially not for passenger vehicles, just like Tesla. So we can keep the gearing simple. We can work with a single speed planetary gearbox, combine it with our motor, which is compact by design, and deliver as such a very compact, complete system. So if you look at the next slide, 3 situations where the compactness of our axial flux motors benefited the customer significantly. So in this case, a P2 hybrid application, could also be a P4, where the space for the motor, available space, was only limited to around 80 millimeters or so. So it was only possible with a yokeless axial flux motor to still deliver that amount of torque in such a small space envelope. So the axial length has to be kept very limited, and that's the perfect situation for a yokeless axial flux motor basically. In the middle you can see a coaxial design where we are using the available space inside the motor, the hollow axis, to our benefit. 2 shafts, a fast rotating shaft together with the motor, and a slow rotating shaft which is spinning at the same pace as the wheels, and a reduction gear. So as a result, a very compact coaxial design where no lay shaft is necessary. This resulted in what we call the MIG module, motor inverter gearbox, or an E-axle module, where we basically put the axial flux motor in the middle. At one end we integrate a silicon carbide inverter, and at the other end we integrate a single speed planetary gearbox, resulting in a very compact package, similar in size as one radial flux motor, but in our case motor, inverter and gearbox all combined together. So that gives a lot of freedom for OEM tier 1 to be more creative in terms of powertrain design, combine different modules in a vehicle. Could be 1 coaxial or lay shaft, could be 2, could be 3, could be 4, to go to a very compact and lightweight situation. If you look at the example here from e-tron, the Audi e-tron, it's quite similar setup, 2 modules where inverter gearbox and single stage planetary gearbox are combined together, but Audi, due to the longer length of the radial flux motor, had to still integrate an inverter on top of it. In our case, we can put everything in line and still stick within the width of the car, and it basically also results in a significant advantage in terms of weight. So replacing the gearbox, the modules from Audi, which are based on induction motors, by Magnax axial flux permanent magnet motors, results in 70 kilograms lower weight and also much higher efficiency, because the fact that we are lower in iron losses and we work with permanent magnets, which is a significant advantage in terms of efficiency and thus range of the vehicle. So that's a very quick overview of the technology. I'm very interested to hear your questions. Thank you very much.
Thank you very much, Daan Moreels. Very interesting presentation, completely different approach, very impressive, the reduction of weight, and welcome to the studio now.
Thank you very much.
So we have actually two questions from the public. One is from Mr. Schneeweiss, and it's also something I would be interested in. If I'm looking at your design, you actually went for high RPM or moderate high RPM with 12,000 RPMs, and you use a gearbox in itself. And the question of Mr. Schneeweiss is, could this design be used for an in-wheel application? So I'm assuming a real wheel motor where there's no reduction, so where you actually would go more for torque density instead of power density.
I had a pretty unstable internet connection, so I didn't hear your question very clearly. I heard something about in-wheel motors.
Yeah, could your design be used for in-wheel motors?
Yeah. We have created a yokeless axial flux motor for an in-wheel application, in-wheel motor application. And also there we see a significant optimization in terms of weight and power density. But we saw that the possibilities for in-runner motors, and I don't know if I'm coming to, because I see that there's a problem in terms of
yeah, I hear you. It's okay.
Connection.
No.
You hear me? Okay.
Yeah, sounds okay. Yeah.
So it's possible we have created such a solution, but we see that the market is more evolving into smaller packages of high-speed motors, and the cases for in-wheel motors, lower speed, high torque, is very niche. So we are very oriented to high volume production of these motors, where we have significant benefits, as you have already seen. So at the moment we focus on that, but it is technically possible also to create in-wheel motors based on yokeless axial flux motor topologies.
Okay.
It has its benefits.
So the technical person says you should actually switch off your camera, so we improve the quality of the sound too, and now we have seen how you look like, so that's okay, I think. The second question from the public is from Fernando Nuno, and well, I don't know if you've done this comparison, but you showed the efficiency maps of the VLTP, and the question was, how much improvement do you see in cycle efficiency? So if you would run the VLTP cycle on your motors compared to let's say, for example, Tesla M3 benchmark. That's a very specific question, but did you run efficiency cycles over VLTP with your motors and compare it to other motors? So we're hoping that the sound's still there. Daan? It's not. Yeah, okay, so I hear that the connection is lost, and I'm very sorry because it's a very interesting topic. I actually have to say that I personally encountered... Oh, now you're back. Very good. Daan, did you hear the question?
Oh, can you repeat, please?
Yeah, the question was, what if you compared your motor solution, because you showed the efficiency map with the VLTP cycle, so what is the cycle efficiency compared to the cycle efficiency, for example, the Tesla M3 benchmark?
Well, we haven't compared it with the Tesla Model 3 motor, which would be a very interesting case. We did a complete calculation for the BMW i3 motor, which is, of course, an older motor from 2016. But there we saw an optimization of about 8% if you purely look on a motor level. That's purely because of the lower iron losses that we have. And you can see, as you have seen on the efficiency map, is that the efficiency map of the BMW, yeah, it's not perfectly aligned with the VLTP area. So, but yeah, another big advantage, of course, which comes with the motor is the small packaging. And there we have made calculations where we can, if we actually use additional space that we get, thanks to the smaller packaging, that we can go up to 25% more vehicle range. So it's a combination of lower iron losses on the motor level, more space for the battery, and also some influence because of the lower weight of not only the motor, but the complete solution, basically. But comparing it with the Tesla Model 3 would be a very interesting exercise. I should ask that our application engineer to do that.
Yeah, we certainly would look forward to such a result. And a final question from my side. I looked at your torque speed curve with the efficiencies, and I would see that you have a rather, I couldn't see any field weakening region in itself. And I was wondering how good is actually this topology, the axial flux motors with strong permanent magnets for field weakening operations and therefore the single stage gearbox?
Ghent University, which originated our R&D basically from 2008, has done a very detailed research on the comparison in terms of field weakening between radial flux motors and axial flux motors. And the conclusion was that there is not a significant difference in terms of field weakening capabilities. The prototypes that we have created have not included a lot of field weakening yet, but the motors that we are currently developing have a field weakening region usually as from 8,000 RPM. So between 8,000 RPM and 20, because with slightly smaller machines, we can go up to 20,000 RPM also. That will be a field weakening area.
Okay.
Yeah.
And I really think there would be a lot of more questions, also especially for your cooling topology using. You said direct, or you said oil cooling. Is it direct oil cooling, or you have cooling? Yeah. Oh, it's direct oil cooling.
So we have two concepts. One concept is air cooling and water cooling, which is similar design. That's not really direct cooling. We still use something in between, but for oil cooling, it's actually oil flowing along the wires, which is very direct cooling, of course. Yeah.
And very efficient in that case. Yeah.
And very effective. Yeah. That's also results in the high power density of the motors.
Yes. Thank you very much, Daan. Very interesting. I'm sure you're available for further questions also, either through the chat or via email. And so we're actually closing now this first, a little bit out of the normal scope session.